teacher, Nabil Kleinhez, who's working with Transistor as our class.
All right. Good morning, everyone. Thanks for coming, and thanks to the Cope for giving me this opportunity to present and for the support, obviously. Today, I'm just going to share a little bit about some of the work I've been doing with poly-3-hexyldiaphene, which we've already seen a little bit about today. And this is a polymer that's conjugated and has this solubilizing chains for solubility in organic solvents. So you can process it from organic solutions like chloroform and trichlorobenzene, toluene, these types of solvents that then allow you to print these electronics. So this is a desirable characteristic of these materials. But in particular, this liquid crystal phase that we've seen in P3HT is something that's interesting. We've seen that it forms by self-assembly and then alignment by capillary flow. And so why is the ordering of the P3HT important? Well, this little animation that my colleague Jiwon back there made, it shows that this intra-chain charge transport is important. But also, when you bring these multiple polymer chains together, the inter-chain charge transport is actually one of the dominant mechanisms for large-scale charge transport over a device that's, say, microns long. You have electrodes separated by microns. So one thing that this does is this ordering improves that charge carrier mobility. So if we can improve that parameter, then we'll see improvements in performance in our devices like transistors, organic light-emitting diodes, and solar cells. So one thing that we wanted to look at was liquid crystals as another solution to achieving this ordering. Because if you notice, like in a crystalline material, obviously these charges will transport very well through that material. Whereas if you have something that's very disordered or isotropic, then the charges will not be able to hop from one chain to another very effectively. On the other hand, in reality, we do have polycrystalline materials a lot of the time. So we don't get these perfectly crystalline materials. Over a large scale, you have these multiple grains. And these barriers between these grains actually act as, they are barriers for the charge transport through the material. So what if we can take a liquid crystal, which is kind of intermediate ordering? So in this case, you have something that's not isotropic, but not perfectly crystalline. We have something in between that's this nematic phase. And in a lyotropic liquid crystal, that can be achieved with an increase in concentration of your material. And so we're going to try to do this with P3HT, and if we can achieve these ordered materials, then we'll have improved performance in these OFETs, these transistors. So that avoids these grain boundaries that you see in perfectly crystalline materials, but you still have this long-range ordering. So one way to kind of characterize this long-range ordering is to use this polarized optical microscopy. So here's a schematic where you have two crossed polarizers, and then in between you have your sample, which has some anisotropy or some kind of order to it. And if it was completely disordered, clearly the light that's polarized in this direction would not pass through the perpendicularly oriented analyzer. So it would just be black on the other side. But if you do have an ordered material, due to the two different refractive indices, you will have a bright image that appears through this analyzer. And you can see here, what we did with P3HT solutions was increase the concentration to very high, 6.6 weight percent. That's about 100 milligrams per mil, which is the most you can get out of this particular P3HT. And this is in trichlorobenzene. What you can see is as you fill a capillary tube with this solution, and then you rotate it between these polarizers, you can see that there's these completely dark and then completely bright, repeating pattern as you rotate. And when it's completely aligned with the polarizer, then it's dark. When it's at 45 degrees, then it's brightest. And this indicates that there's definitely some long-range ordering in this solution. Now, what we noticed with that solution was that it only happened if you let the solution age for 20 minutes before you fill the capillary. And what that does is it allows the solution to aggregate. And you can see this color change that happens. If you fill the capillary with this solution, it would be completely isotropic, no ordering. So we wanted to investigate this aging phenomenon a little bit more and how it leads to that ordering. And so if you look at the UV-Vis spectrum, it gives us an indication of the kind of self-assembly that's happening in the solution. And if you see the rise in this low energy peak with the days of solution aging, you can see that the solution the polymer chains are starting to interact with each other, and they're forming these aggregates. And this is the lowest energy 0 to 0 vibrational transition. And you can actually you can sort of deconvolute your UV-Vis spectrum into the aggregate portion via a theoretical Frank Condon fitting and the amorphous component. And then based on that, you can calculate a percent of aggregates. Sorry, that was cut off here. The percent aggregates is on the y-axis, days aging. So you can see it's a pretty linear increase in the percent aggregates in solution. And then correspondingly, we see as we age the solution, and this is a much more dilute solution, by the way. This is not the very concentrated solution we started with. In this case, we're seeing the effect of aging and how important it is to form these nicely ordered birefringent fluids. So it's not just the concentration, it's the amount of time that you let the solution age that really helps you achieve this long-range order in these capillaries. And then we also, to test a little bit of the mechanism behind this, we wanted to see what happens if you take one of these capillaries, heat it up, so it's in the isotropic state, and let it cool back down. Does it reform that birefringence and that ordering? And so far, what we've seen is no, it doesn't. So you can see before and after heating, even waiting for 15 days. So this might indicate that there's actually an alignment process that happens when you flow the solution into the capillary tube. And so that's assisting with forming these ordered fluids. And so you can further quantify the order in these capillaries by using Raman Spectroscopy. And so if you take a regular day 0 solution of P2HC, and then you put it in your capillary, and then you shine your laser from the Raman, which is polarized, onto that sample. No matter what degree of rotation you rotate the sample, that intensity of this CC double bond peak in the polythiophene backbone will not change. So that was what you would expect for an isotropic material. There's no dependence on the rotation. But if you have something that's ordered, then the incoming polarized laser will actually interact differently with the sample at different angles of your stage rotation. And so now you have this varying peak height with the angle. And so you can actually do this for 0 to 360 degrees in both parallel and perpendicular polarizer configurations. And then you can use that data to calculate an order parameter. And so as the solution ages, you can see that this order parameter, which ranges from, well, an isotropic solution would be 0. A perfectly ordered crystal would be 1. But this P2 order parameter is actually increasing fairly clearly with time. So, and we also use dynamic light scattering to also look at the depolarization ratio, which is the ratio of scattered intensity with cross polarizers and parallel polarizers. And we see that there is this increase, which suggests the formation of anisotropic entities in the solution. And then lo and behold, if you do cryo-TEM, so just taking one of these solutions, freezing it very quickly in liquid ethane, so we set this to Tulane for this characterization, we can see that a fresh solution looks rather amorphous, whereas an aged solution clearly shows the presence of these nanofibrils in the solution. So, what does that mean? Well, in solution, maybe it's not very useful for electronics, but if we can evaporate the solvent and see what's left, is it still ordered? And in this case, we were able to achieve some ordering in the film. So this is taking the solution, drawing it out on a glass slide with a micropipette tip, and then seeing that, yes, you can in fact see some ordering as evidenced by the polarized optical microscopy. But we have yet to translate this into the increase in charge carrier mobility. Some preliminary results have shown that solutions that are aged for a very long time can see increases in mobility, but we're still working on further demonstrating that. So, yeah, just to conclude, we have the self-assembly of the P3HT solutions over time. That seems to be facilitating the formation of these ordered birefringent fluids. And that's likely due to the self-assembly of the P3HT into these rod-like entities, which are then aligned through the capillary flow. And we're able to quantify the order parameter by Raman Spectroscopy and show that in cryo-TEM that these fibers do exist in solution, and that the order can be maintained in the solid state when you process it in particular ways. And so, yeah, I'd just like to thank my group and all of our collaborators, Dr. Mohan, Dr. Park, Dr. Russo, Karthik from Material Science, and a few collaborators from LSU, and some undergraduates who did a lot of work on this project. Eugenia, Zongzhe, and Jibao. Jibao is from Tulane, actually. He did the cryo-TEM for us. And yeah, so Jamila, Eugenia, and Zongzhe really helped a lot with this data. And all the other group members for their contributions, and my PhD committee members, and obviously my advisor, Dr. Elsa Rekmanis, and support from the COPE and the NSF and the IGERT and AFOSR for funding. So thanks a lot, and I'll take any questions. Any presentation? Seth?
Did you do any X-ray scattering on these things?
No, we have done X-ray scattering on the capillaries in solution, which showed completely amorphous behavior. So we were not sure if that's because of the presence of the solvent that's still there, that's kind of interfering, but we haven't done X-ray on the films. So we were a little bit, not sure why the solution X-rays didn't show any, crystallinity, but we're
Did you use a synchrotron or?
Yeah.
So you went to argon or something like that?
No, we sent it to Brookhaven.
Other questions? Go up here. Go ahead, Bill.
When you were aging your P3HT, was it exposed to any ambient light or oxygen, or how was that kept during the aging process?
It was kept in the dark. Oxygen would have been there because it's just in a sealed vial in the room. We didn't remove the oxygen, but this, yeah.
Just on the slide on the Raman, so you're saying that the graph on the right, you're seeing the different peak levels because of the orientation of the carbon-carbon bonds. But shouldn't your orientation of your agglomerates be isotropic as well in the solution? So even when you're rotating it, it should feel
Well, the fibers themselves, this is indicating that the fibers are aligned, that there is an overall orientation in the solution.
So were these Ramans on the millimeter vial?
Yeah, the millimeter
okay.
capillaries.
Okay.
Yeah.
I have a question. Can you actually accelerate this by doing some sonication or some of the work that one of your predecessors?
Yeah, actually, it's interesting with the sonication. You can do this, but then I don't see the same ordered solution. Yeah, so preliminary results suggest that there is an effect on how long these fibers are, perhaps, because sonication tends to produce shorter fibers, and so that seems to not align as well. But there's other ways we can add porous solvents. We've done a little bit of that. Change the temperature. So yeah.
Great. Well, thank you. Let's thank Nabil.